At the heart of every galaxy lies a cosmic monster. Supermassive black holes are not just empty voids, but the architects of reality itself. By the end of this journey, you will know the 50 most profound secrets that govern these invisible giants. We will uncover how they might be gateways to other universes and why they sing with the rhythm of a cosmic heartbeat. What is the one cosmic mystery you hope we finally solve? The first secret shatters our view of these cosmic monsters as mere destroyers. They are the anchors that hold galaxies together. Picture a billion stars swirling in a vast cosmic dance. Without a supermassive black hole at the center, that dance would dissolve into chaos. Its immense gravitational pull is the unseen hand that guides the orbits of every star, every planet, every speck of dust. This invisible giant dictates the grand architecture of its galactic home, preventing it from simply flying apart into the void. But the connection runs even deeper. Astronomers have uncovered a strange and profound correlation. The mass of the central black hole is mysteriously linked to the properties of the galaxy itself, specifically the speed of the stars swirling in its outer bulge. A larger black hole means a faster-moving stellar population. This is not a coincidence. It is a fingerprint of a shared history, a deep, co-evolutionary relationship where the growth of the black hole and the birth of the galaxy are intimately entwined. One did not simply form inside the other. They grew up together, their fates locked in a gravitational embrace from the very beginning. This profound connection forces us to confront the second great secret. The name black hole is a cosmic misnomer. They are not empty holes in space. They are the exact opposite. Imagine taking the entire mass of our sun, a colossal sphere over 800,000 miles across, and crushing it down into a single point. That point, a singularity, possesses such an extreme density that it warps the fabric of space and time around it into a bottomless pit. This is the true nature of a black hole, not a void, but an object of almost incomprehensible mass and density. The darkness we associate with it comes from a boundary known as the event horizon. Think of this not as a solid surface you could touch, but as the ultimate point of no return. It is the invisible line where the gravitational pull becomes so overpowering that not even light, the fastest thing in the universe, can achieve escape velocity. Once anything crosses this threshold, it is lost forever to our observable reality. Its information severed from the rest of the cosmos. But what is truly bending to create this trap? It is spacetime itself. The singularity's immense gravity does not just pull on objects. It warps the very stage upon which the universe plays out. Space becomes curved like a stretched rubber sheet with a bowling ball at its center, and time slows to a crawl. This warping is so severe within the event horizon that all possible paths for matter and energy lead inward toward that central, infinitely dense point. There is no outward direction left to travel. So how do you find something that emits no light at all? The third secret reveals our methods for hunting these invisible behemoths. We cannot see the black hole itself, so we must become cosmic detectives, observing the frantic activity of everything caught in its gravitational grip. At the center of our own Milky Way galaxy, astronomers have performed a stunning feat of observation. They have tracked the orbits of individual stars whipping around an empty, dark point at speeds exceeding 3 million miles per hour. One star, known as S2, completes a full orbit in just 16 years, tracing a path that proves an object 4 million times more massive than our Sun must be lurking in that central void. We call this object Sagittarius a star, the supermassive black hole at the heart of our galactic home. Another powerful clue comes from the black hole's feeding habits. When a black hole actively pulls in gas and dust, this material does not fall straight in. It forms a swirling, superheated maelstrom known as an accretion disk. Friction within this disk heats the material to millions of degrees. causing it to glow with intense radiation across the entire electromagnetic spectrum, from X-rays to radio waves. We see this brilliant, violent halo of light surrounding the central darkness, a telltale sign of a monster's meal. And now, a revolutionary new sense has been added to our cosmic toolkit, gravitational wave astronomy. When two supermassive black holes eventually spiral together and merge, they do not create a flash of light. Instead, they shake the very fabric of space-time, sending out ripples known as gravitational waves. These waves are like cosmic tremors, stretching and squeezing everything in their path as they travel across the universe. By building detectors sensitive enough to feel these minuscule vibrations, we are listening to the echoes of colossal collisions that happened billions of years ago, confirming the existence of black holes we could never hope to see. But these gravitational detectives now face their greatest challenge. The fourth secret asks a question that seems almost too fundamental to answer. Where did these cosmic giants come from in the first place? Their origin story is one of the deepest puzzles in modern astronomy. We are forced to look back to the very dawn of time, to an era just a few 100 million years after the Big Bang, to find clues. The leading theory suggests they began as the remnants of the first generation of stars. These were not like the stars we see today. They were true behemoths, hundreds of times more massive than our Sun. They lived fast and died young, exploding in catastrophic supernova and leaving behind black hole seeds. Yet there is a problem with this story. For a star-born black hole to grow to supermassive proportions, weighing billions of times the mass of our Sun, it would have to feed at a ferocious, almost impossible rate for the entire age of the universe. It is like trying to grow an ancient, 1,000-year-old redwood tree from a tiny seed in just a few decades. The math struggles to make it work. This forces us to consider a far more dramatic birth. What if the first supermassive black holes did not come from stars at all? Another theory proposes the direct collapse of primordial gas clouds. In the dense, hot soup of the early universe, vast clouds of gas could have collapsed under their own immense weight, skipping the star-forming stage entirely and condensing directly into a massive black hole seed. This would create a giant from day one, a ready-made anchor with a huge head start on growth. This brings us to the ultimate cosmic chicken and egg problem. Did the galaxy form first, with a black hole eventually taking root at its center? Or did the black hole form first, its powerful gravity acting as a seed around which an entire galaxy would slowly coalesce? The mysterious correlation between a black hole's mass and its galaxy's properties hints that the answer is not so simple. They likely grew up together, each influencing the other's development in a complex gravitational dance. The black hole was not just a resident of the galactic city, it was the foundation upon which the city was built. This feeding frenzy, however, is not a constant state. The fifth secret reveals that these cosmic monsters have distinct moods, cycling between deep slumber and violent, active outbursts. When a black hole is actively pulling in gas and dust, it is in a state known as accretion. This material does not fall in silently. It spirals into a vast, flat and frantic disk, a whirlpool of superheated matter orbiting at nearly the speed of light. The immense friction and gravitational forces within this accretion disk heat the gas to millions of degrees, causing it to shine with a brilliance that can outshine every star in its host galaxy combined. This is a black hole in its feeding phase, a beacon of terrifying power. But the most astonishing part is what happens next. For a long time, we thought black holes were the ultimate cosmic vacuums, consuming everything that crossed their path. The truth is far more strange and impactful. They do not just feed, they also burp. During these active phases, a black hole does not consume all the material drawn into its accretion disk. Intense magnetic fields and radiation pressure can launch a significant portion of the incoming gas and dust back out into space at tremendous speeds. These are the cosmic burps, powerful outflows of energy and matter that can travel for tens of thousands of light years. These outflows are not gentle breezes. They are colossal jets and winds that carve through the galaxy, and they play a critical role in galactic evolution. By blasting away the raw material for new stars, the cold gas and dust within galactic clouds, the black hole effectively regulates the rate of star formation across its entire domain. It is a cosmic self-regulation system. A voracious feeding phase leads to a powerful burp, which then shuts down the very process that fueled the feast, sending the black hole back into a quiet, quiescent state. This cycle of consumption and expulsion means the black hole is not just a passive anchor at the galaxy's heart. It is an active governor, its immense appetite directly controlling the growth and future of its stellar city. These powerful cosmic burps can sometimes focus into something even more extreme, the sixth secret, the phenomenon of relativistic jets. When conditions are just right, a feeding supermassive black hole does not just expel gas in a wide wind. It can fire off twin beams of pure energy and matter, narrow and precise, that scream across the cosmos at nearly the speed of light. These are not gentle streams. They are the most powerful particle accelerators in the universe, and their source is a complex dance between the black hole's immense gravity and its own rotation. The engine for these jets is not the black hole itself, but the frenzied material within its accretion disk. As superheated plasma swirls at incredible velocities, it generates immensely powerful magnetic fields. These fields become twisted and wound up by the black hole's own spin, a property it gains from all the matter it has ever consumed. Think of a figure skater pulling their arms in to spin faster. The black hole does the same with the material it pulls in, and this stored rotational energy is phenomenal. The wound-up magnetic fields act like the barrel of a cosmic rifle, channeling some of the infalling material and accelerating it outward along the black hole's rotational axis, the only path of least resistance. The result is a pair of jets erupting from the poles of the system, shooting directly away from the accretion disk. The scale of these structures is almost impossible to grasp. They can stretch for millions of light years, far beyond the boundaries of their home galaxy, punching into the vast, empty spaces between galaxies. We can see them because the particles within these jets, moving at such relativistic speeds, give off a brilliant glow across many wavelengths, from radio waves to powerful gamma rays. They are cosmic lighthouses, their beams visible from across the universe, and they carry enough energy to heat the sparse gas between galaxies, effectively influencing the climate of intergalactic space itself. These relativistic jets are a testament to the raw power locked within a spinning black hole, but that power warps more than just space, it twists time itself. The seventh secret is one of the most mind-bending consequences of Einstein's theory of relativity, a phenomenon known as time dilation. Gravity does not just bend the paths that objects follow. It also stretches the very fabric of time. The stronger the gravity, the slower time flows. At the edge of a supermassive black hole's event horizon, where gravity is at its most extreme, this effect becomes truly dramatic. Imagine a pair of twins. One is a brave astronaut who volunteers to travel towards the event horizon, while the other stays in a safe, distant spacecraft to observe. As the adventurous twin gets closer and closer to the point of no return, a strange thing happens from the observing twin's point of view. The astronaut's movements, their heartbeat, even the ticking of their clock would all appear to slow down. They would move in an agonizing, slow-motion crawl toward the darkness. For the observer watching from afar, it might take thousands or even millions of years for the astronaut to finally cross the event horizon. But here is the truly bizarre part. For the astronaut falling in, their own experience of time would feel completely normal. Their clock would tick at its usual rate. Their heartbeat would feel regular. They would cross the event horizon in what, to them, feels like a finite and perhaps surprisingly short amount of time. This is not an illusion or a trick of light. Time itself is flowing at different rates for the two individuals because they are experiencing different strengths of gravity. A simple analogy can help make sense of this cosmic strangeness. Think of the universe as a vast, stretchy rubber sheet. A heavy object like a black hole creates a deep well in this sheet. Now picture time as a tiny ball rolling across the sheet. On the flat, distant regions, the ball rolls quickly, but as it approaches the steep slope of the gravity well, its roll slows down dramatically. The ball itself does not feel like it is moving any slower, but from our perspective on the flat part of the sheet, its progress has nearly halted. This is the reality near a supermassive black hole. Time grinds to a near standstill at the event horizon from an outside view, creating a cosmic cliffhanger that, for the falling object, has already concluded. This rhythmic warping of time is matched by a literal rhythm emanating from the edge of the void. The eighth secret reveals that these cosmic monsters can sing. The song is not carried on sound waves, for sound cannot travel through the vacuum of space. Instead, it is a rhythmic pulse of intense X-ray light, a cosmic melody broadcast across the universe. This phenomenon is known as a quasi-periodic oscillation. The source of this song is the superheated material in the black hole's accretion disk. As gas and dust spiral inward at tremendous speeds, they do not flow smoothly. The disk can become unstable, with pockets of material vibrating and oscillating under the black hole's immense gravitational pull. These vibrations create regular, repeating patterns in the X-ray light we observe, like the steady beat of a drum or the rhythmic thumping of a heart. For a supermassive black hole, this beat is incredibly slow, with each pulse taking hours or even days to complete. Scientists listen intently to these cosmic songs because the specific rhythm holds vital information. The frequency of the oscillations, the speed of the beat, is directly linked to the mass and the spin of the black hole itself. A more massive black hole has a deeper gravitational well, which creates a slower, lower frequency beat. A rapidly spinning black hole, warping spacetime around it even more severely, can alter the rhythm in distinct ways. By carefully analyzing the tempo and structure of these X-ray melodies, astronomers can effectively weigh a black hole and measure how fast it is spinning, all from a safe distance across interstellar space. It is a form of cosmic musicology where every note in the black hole's song tells a story about the nature of the invisible singer. Even the song of a black hole must eventually fade. The ninth secret confronts a paradox so profound it threatens to rewrite the fundamental laws of physics. This is the information paradox, a puzzle born from the work of Stephen Hawking. He made a startling prediction that black holes are not entirely black. They can, over unimaginable eons, slowly evaporate. This happens through a strange quantum process occurring right at the event horizon. Empty space is not truly empty. It is a seething foam of virtual particles, pairs of matter and antimatter that constantly pop into existence and then annihilate each other almost instantly. But at the edge of a black hole, gravity is so intense that it can tear these particle pairs apart. One particle falls into the abyss while its partner escapes into space. The escaping particle becomes real, carrying away a tiny bit of the black hole's energy. This slow, steady leak is Hawking radiation. Over trillions upon trillions of years, this process would cause the black hole to lose mass and ultimately vanish in a final puff of particles. This leads to the heart of the paradox. What happens to all the information about the things that fell in? Think of a book thrown into a fire. The book burns to ash, but in principle, a physicist with perfect knowledge could analyze the smoke and the ashes and reconstruct every word on every page. The information is scrambled, but it is not destroyed. Quantum mechanics insists that information must always be preserved. It is a fundamental rule of reality. Yet, if a black hole evaporates completely, leaving behind only a random, featureless spray of Hawking radiation, then all the detailed information about every star, every planet, every atom that ever crossed its event horizon would be lost forever. It would be as if you burned that book and the ashes themselves disappeared, leaving no trace that the book ever existed. This is the information paradox. The smooth, predictable laws of general relativity that govern black holes seem to demand that information is destroyed, while the rules of quantum mechanics demand it must be saved. Both theories cannot be correct. This conflict points to a deep flaw in our understanding, a crack in the foundation of physics that suggests our current picture of reality, especially our picture of the event horizon, is profoundly incomplete. The resolution to this paradox might be the key to a deeper truth, a theory of everything that finally unites gravity with the quantum world. This cosmic puzzle of lost information leads us to a possibility that seems ripped from science fiction. The 10th secret proposes that some supermassive black holes might not be in points at all. They could be wormholes, cosmic bridges tunneling through the fabric of spacetime to another place, or even another universe entirely. The theoretical foundation for this comes from the equations of general relativity itself. Einstein's math allows for the existence of these shortcuts, known as Einstein-Rosen bridges. While a traditional black hole is thought to contain a singularity, a point of infinite density from which there is no return, a wormhole would have a different internal structure. It would be a tunnel or a throat connecting two distant points. You would not be crushed into nothingness at the center. Instead, you would, in theory, pass through the gateway and emerge somewhere else entirely. The entrance would look almost identical to a black hole's event horizon, a point of no return, but the destination would be a white hole, a theoretical region of spacetime where matter and energy can only exit, never enter. It would be like a cosmic geyser, spewing out everything that fell into the connected black hole on the other side. This is where the information paradox finds a potential, though highly speculative, solution. Perhaps information is not destroyed inside a black hole. Maybe it is simply transported elsewhere, preserving the fundamental laws of physics. How could we ever tell the difference between a destructive monster and a cosmic gateway from the outside? The key might lie in the black hole's spin. Some models suggest that a rapidly rotating supermassive black hole could have a ring-shaped singularity instead of a point. This ring, theorists propose, could be the stable entrance to a wormhole's throat. The intense centrifugal force of the spin might keep the tunnel open, preventing it from instantly collapsing. If we could somehow measure the internal structure of a black hole and detect the signatures of this ring-like gateway, we might have our first clue. Of course, this remains one of the most speculative ideas in all of physics. No evidence currently exists to prove that wormholes are real, let alone that supermassive black holes are hiding them. The energies required to create or stabilize one are beyond anything we can comprehend. Yet, the mere mathematical possibility opens a breathtaking vista. The anchors at the heart of every galaxy might not be final graves. They could be the grand central stations of the cosmos, connecting a vast network of realities we have only just begun to dream of. The scale of these cosmic gateways can become almost unimaginable. Our own galaxy's black hole, Sagittarius, a star, is a giant at 4 million solar masses, but it is a mere pebble compared to the true titans that lurk in the cosmic deep. The 11th secret exposes the existence of ultramassive black holes, behemoths so large they defy our understanding of how such things are even possible. These are not merely supermassive. They are monsters with masses measuring tens of billions of times that of our Sun. One of the most famous resides at the heart of a galaxy called Home 15A, a colossal beast estimated to weigh in at around 40 billion solar masses. To put that into perspective, if you place this single object at the center of our solar system, its event horizon would extend far beyond the orbit of Pluto, swallowing our entire planetary system with room to spare. Finding these giants is a challenge in itself. They typically dwell in the cores of the universe's largest galaxies, which are often found at the centers of immense galaxy clusters. These are the retired titans of the cosmos, galaxies that have stopped forming new stars and have grown vast through eons of cosmic cannibalism, consuming their smaller galactic neighbors. The black hole at the center has grown fat from this endless feast. The very existence of these ultramassive black holes poses a serious challenge to our models. How did they get so big so fast? Even with the direct collapse model, growing to 40 billion solar masses in the relatively short age of the universe pushes the limits of physics. They would have needed to feed at their maximum possible rate for billions of years, a sustained gluttony that is difficult to explain. There is also the mysterious process known as dynamical friction to consider. When two galaxies merge, their central black holes eventually spiral toward the new core. As they do, they slingshot stars away, clearing out the galactic center. In the most massive galaxies, this process can create a vast star-poor core, a region of strangely dim light. It is in these dark, evacuated cores that the ultramassive black holes often reign supreme. Their own violent histories have scoured their immediate surroundings, leaving them isolated in a gravitational throne room of their own making. Their immense size suggests they are the ultimate products of a cosmic hierarchy, the final winners in a universe where giants consistently devour the small. Yet their sheer mass forces us to question if we are missing a piece of the puzzle, perhaps an earlier, more efficient method of growth that has since vanished from the universe. These ultramassive giants, however, do not always feed in silence. The 12th secret reveals that even the most dormant black hole can violently awaken, hiccuping with a flash of cosmic light. This happens when a star, going about its normal orbit, wanders just a little too close to the gravitational abyss. The star is about to experience a tidal disruption event. As the star approaches, the black hole's gravity does not pull evenly on it. The side of the star closest to the monster feels a vastly stronger tug than the side facing away. This difference in force, the tidal force, stretches the star horribly. It is like the difference between the moon's pull on the near side of Earth creating the ocean's high tide, but amplified to an almost unimaginable extreme. The star cannot hold itself together. It is stretched lengthwise into a long, thin stream of superheated gas, a process poetically called spaghettification. This stream of stellar material doesn't just vanish. It wraps around the black hole, forming a temporary, frantic accretion disk. The sudden infusion of fresh fuel ignites a brilliant flare of light that can outshine the combined output of every star in its galaxy for several months. This is the black hole's hiccup, a sudden, bright burp of energy signaling a stellar feast. For astronomers, a tidal disruption event is a precious and dramatic opportunity. It is like a flashbulb going off in a dark room, illuminating the invisible monster at the center for a brief, glorious moment. By studying the rise and fall of this light, scientists can measure the black hole's mass and spin. They can watch the physics of accretion unfold in real time, from the initial shredding of the star to the final fading of the flare. Each hiccup provides a unique laboratory to test the limits of gravity and witness the raw, destructive power that governs the galactic core. That brilliant flare from a shredded star is a rare and violent spectacle. The 13th secret reveals a far more common, yet hidden, reality. For every one of those actively feeding monsters we can easily spot, there are thousands, even millions of others lying dormant. Our own galactic center, Sagittarius, a star, is a perfect example of this quiet majority. It is not actively feeding, not powering brilliant jets, not singing a loud X-ray song. It is a sleeping giant. This dormancy is the default state for most supermassive black holes across cosmic time. They are the rule, not the exception. This presents a monumental challenge for astronomers. How do you take a census of something that is, by its very nature, invisible and silent? We can only reliably find them if they are close enough for us to track the orbits of stars around them, as we did with Sagittarius, a star, or if they are actively accreting material and glowing brightly. For distant galaxies, the stellar orbit method becomes impossible. We are left searching for the faint, quiet ones, the sleeping dragons in the dark. This means our current map of supermassive black holes is profoundly biased. We have a detailed understanding of the loud, active ones, but we know very little about the silent population that makes up the vast bulk of these cosmic anchors. Their hidden nature forces us to ask fundamental questions. What does a dormant black hole actually do? Is it truly inert, or is it subtly influencing its galaxy in ways we are only beginning to sense? Even in its sleep, its immense gravity still dictates the motions of the stars at the very core. It is a silent king on a gravitational throne, its presence felt even when it is not actively ruling through violent outbursts. This hidden population is the true cosmic norm, a universe filled with sleeping giants, each holding the potential for a future awakening that could reshape its entire galactic domain. That silent, invisible presence still manages to announce itself in a strange and beautiful way. The 14th secret is that these cosmic monsters warp the very light traveling past them. A supermassive black hole's gravity is so immense that it does not just trap matter. It bends the fabric of space itself, and since light travels in straight lines through that fabric, its path gets curved. This phenomenon is called gravitational lensing. Imagine a perfectly flat, taut rubber sheet representing space. Now place a heavy bowling ball in the center. The sheet dips dramatically. If you roll a tiny marble across the warped sheet, its path will curve around the heavy object. Light behaves in exactly the same way around a black hole. The light from a distant star, traveling for millions of years to reach us, will have its path bent as it passes near the black hole's gravitational well. From our perspective, that background star will appear to be in a slightly different position in the sky than it actually is. The black hole's gravity is acting like a flawed lens in a colossal cosmic telescope. Sometimes, when the alignment is perfect, the effect becomes even more spectacular. Instead of just shifting a star's position, the black hole can create multiple images of the same background galaxy, or stretch it into a brilliant, luminous arc known as an Einstein ring. It is a perfect circle of distorted light encircling the central darkness, a ghostly halo created by the ultimate cosmic illusionist. For astronomers, this is not just a pretty picture. It is a precision tool. By measuring how much the light is bent, scientists can literally weigh the black hole causing the distortion. The degree of the lensing effect directly reveals the mass of the invisible object. This provides a completely independent way to measure a black hole's heft, confirming the estimates we get from watching stars orbit. Furthermore, this cosmic illusion provides one of the most stringent tests of Einstein's theory of general relativity. The theory makes very specific predictions about exactly how much the light should bend. Every time we observe gravitational lensing and the measurements match Einstein's equations with perfect accuracy, it is another triumph for a theory conceived over a century ago. The darkness at the galactic center, by twisting the light of distant suns, continues to prove the strange and wonderful warping of our universe. The darkness at the galactic center can spin. This is the 15th secret, the hidden rotation that transforms a passive gravitational pit into a dynamic cosmic engine. We call this a Kerr black hole, named for the mathematician who found the solution in Einstein's equations. Its spin is not like a planet's simple rotation. A spinning black hole does something far stranger. It grabs the fabric of spacetime itself and drags it around in a swirling, inescapable vortex. This phenomenon is known as frame dragging. Imagine stirring a cup of coffee. The liquid closest to the spoon is pulled along most strongly, creating a whirlpool. Now replace the coffee with the very fabric of reality and the spoon with a billion solar mass black hole. space and time are forced to rotate with the monster, creating a cosmic maelstrom just outside the event horizon. This region, called the ergosphere, is where frame dragging becomes so powerful that nothing can remain stationary. Every object caught there is compelled to move, swept up in the current of spinning spacetime. Measuring this spin is one of the most difficult tasks in astronomy. We cannot see the black hole itself, so we must observe the behavior of the matter it has captured. One method is to study the inner edge of the accretion disk, that brilliant whirlpool of superheated gas. For a non-spinning black hole, this disk can only spiral inward so far before it plunges into the abyss. But a rapidly spinning black hole, with its frame-dragging effect, can pull the fabric of space so forcefully that the accretion disk can orbit much closer to the event horizon. By measuring the X-rays emitted from this innermost stable orbit, astronomers can calculate how tightly space is being wound up and thus determine the black hole's spin. Another clue comes from those colossal relativistic jets. The energy to power these universe-spanning beams seems to be drawn directly from the black hole's rotation. A faster spin means more rotational energy is available to be tapped by the twisted magnetic fields, resulting in more powerful and focused jets. The spin is the battery, and the jets are the brilliant discharge of its stored power. This property is crucial because it dictates the black hole's potential for violence and influence. A supermassive black hole with a high spin is an efficient engine, capable of converting the mass of swallowed stars into staggering amounts of energy, which it then projects across the cosmos through its jets. A black hole with little to no spin is a far less efficient consumer, a sluggish giant whose meals produce less fanfare. The spin is a fossil record of its history, shaped by every merger and every meal. Did it grow by steadily pulling in gas from one direction, spinning it up like a top? Or was it built from chaotic mergers with other black holes, collisions that could have sent it tumbling in any direction? The answer is written in its rotation, a hidden signature of its past etched into the warped space around it, governing the fury it can unleash upon the galaxy. That same gravitational slingshot that can tear a star apart can also launch one into the void forever. The 16th secret is that supermassive black holes are the ultimate cosmic catapults, creating the fastest stars in the entire universe. These are the hypervelocity stars, lone suns hurtling through the emptiness between galaxies at speeds exceeding 1,000,000 miles per hour. Their origin story requires a stellar partnership and a close encounter with doom. Imagine a binary star system, two suns locked in a mutual orbit, drifting perilously close to the central black hole. The immense gravity of the monster disrupts their delicate dance. In a gravitational maneuver known as the Hill's mechanism, the black hole violently seizes one star, capturing it into a tight, doomed orbit. Its partner, however, receives a tremendous slingshot effect, a gravitational kick so powerful that it is flung away at a staggering velocity, fast enough to completely escape the gravitational pull of the entire galaxy. It becomes a cosmic runaway, a lone traveler on an endless journey into the intergalactic dark. We have actually caught these runaways in the act. One of the first discovered, a massive blue star speeding through the outskirts of our Milky Way, was tracked moving so fast that its trajectory pointed directly back to the galactic center, like a forensic clue pointing to the scene of the crime. These stars are more than just celestial curiosities. They are living proof of the violent processes occurring in the dense stellar environments around supermassive black holes. Each hypervelocity star we discover is a tracer bullet, its path and speed revealing secrets about the gravitational landscape and the population of binary stars that dare to wander too close to the ultimate slingshot. Such incredible violence and complexity somehow leads to a place of profound simplicity. The 17th secret reveals that black holes, for all their cosmic power, are among the most basic objects in the universe. This is the essence of the no-hair theorem. The name is a playful but deeply meaningful metaphor. It suggests that a black hole has no distinguishing features, no frizz or flare, no individual style, just like a head that has been completely shaved bare. No matter how complex the object that falls in, whether it is a planet made of iron, a star made of hydrogen, or an entire spacecraft built from 1,000 different alloys, the black hole itself does not care. It forgets the entire history and composition of whatever it consumes. All of that intricate information is lost behind the event horizon, leaving the black hole fundamentally unchanged in its core identity. According to this theorem, you can describe any black hole in the entire cosmos with just 3 simple numbers: its mass, its electric charge, and its spin. Mass tells you how strong its gravitational pull is. Spin tells you how fast it is rotating and how it drags spacetime around with it. Electric charge is usually negligible, as black holes tend to be almost perfectly neutral, attracting equal amounts of positive and negative particles that cancel each other out. So in practice, most black holes are defined by just 2 properties: how much they weigh and how fast they are turning. Think of it like this. You can describe a perfectly smooth, featureless ball with just one number: its diameter. A black hole is only slightly more complex, requiring just 2 or 3 numbers to tell you everything there is to know about its gravitational influence on the outside universe. This is a staggering simplification. A single star, before it collapses, has an incredibly complex structure with different layers, magnetic fields, and chemical compositions. But once it crosses the threshold and becomes a black hole, all of that beautiful complexity is erased, reduced to a mere few digits. It is the ultimate cosmic eraser, not just destroying matter, but obliterating information itself, leaving behind a gravitational signature that is hauntingly simple and pure. This mathematical elegance is beautiful, but it also creates a deep tension with the laws of quantum mechanics, which insist that information can never be truly lost. The smooth, featureless black hole of the no-hair theorem seems to violate this fundamental rule, pointing once again to the unresolved conflict at the heart of modern physics, a conflict where the very simplicity of the void becomes its most profound and puzzling secret. Our galaxy is not a solitary island, but one city in a vast cosmic archipelago. Just as cities can merge into sprawling megacities, galaxies themselves collide. This brings us to a spectacular secret: the existence of binary supermassive black holes. When 2 galaxies merge, their central giants are drawn together by gravity, becoming trapped in an orbital dance. At first, they are separated by thousands of light years, each holding sway over its own retinue of stars. They begin a slow, stately waltz that can last for hundreds of millions of years. As they orbit, their immense gravitational pull slingshots stars away into the darkness, a process that steadily steals energy from the pair, causing them to spiral ever closer. This cosmic dance floor gradually empties, leaving the 2 titans in an increasingly intimate embrace. For a long time, they continue their orbit, a pair of invisible monsters circling a common center of gravity. We have found evidence of these duos by spotting the unique, wobbling jets erupting from a single galactic core, a sign that not one, but 2 powerful engines are at work, tugging at each other. We also see quasars, those brilliant beacons powered by feeding black holes, that flicker with a rhythm suggesting 2 separate hearts are beating at their center. But this dance cannot last forever. The final act of this billion-year performance is a cataclysm of unimaginable scale. As the black holes draw within just a few light years of each other, they begin to lose energy not just by scattering stars, but by rippling the fabric of spacetime itself. They stir the cosmos around them, emitting gravitational waves. These ripples in reality carry away the final bits of their orbital energy, tightening their spiral in a final, furious descent. When they finally merge, the event is one of the most powerful in the universe since the Big Bang. For a brief moment, the collision releases more energy than all the stars in every galaxy in the observable universe combined. This energy is not in light but in a final, deafening crescendo of gravitational waves, a cosmic shout that rings out across billions of light years. This is the fate of all such pairs, a violent union that forges a single, even more massive black hole, a new anchor for a new, combined galaxy. That brutal simplification of matter into pure mass and spin brings us to a secret that challenges every science fiction movie you have ever seen. The event horizon is not a solid surface. There is no cosmic guardrail, no physical wall of swirling darkness to crash into. For an astronaut falling feet first toward a supermassive black hole, crossing this infamous boundary would be an utterly uneventful, silent transition. The event horizon is not a thing you can touch. It is a location in space-time, a mathematical point of no return defined entirely by gravity's grip on light. You would not feel a jolt, see a flash, or hear a sound as you passed from the observable universe into the black hole's hidden interior. The coordinates of space and time simply swap their roles, making forward motion toward the singularity as inevitable as the passage of time itself. Yet this lack of drama is the most terrifying part. Long before you reach that invisible threshold, you would have already been destroyed. The real danger is not the event horizon, but the tidal forces. These are the differences in gravity's pull across the length of your body. Your feet, being closer to the black hole, would feel a vastly stronger gravitational pull than your head. For a stellar mass black hole, this difference is so extreme and happens so close to the event horizon that it would stretch you into a long, thin stream of atoms in an instant, a process we call spaghettification. But for a supermassive black hole like Sagittarius, a star, the event horizon is so far from the central singularity that the gradient of gravity is much more gentle. You could theoretically cross the event horizon intact. The spaghettification would happen deep inside, a private doom that the outside universe would never witness. From the perspective of someone watching from a safe distance, your image would appear to freeze at the event horizon, redden, and fade away over millennia, a ghost forever approaching a line you crossed in a single, silent moment. The true horror is not a collision with a barrier, but the serene and certain knowledge that every possible path now leads inward, and that the clock counting down to your inevitable end has already started, its ticking felt only by you. The silent, sleeping giants are not always passive. Their most profound influence on the galactic landscape occurs not in their slumber but in their violent awakenings. This feedback loop is a key secret to understanding why some galaxies are red and dead, vast cosmic graveyards where star formation has ceased. The process begins when a supermassive black hole enters an active feeding phase. As gas funnels into the accretion disk, it heats to incredible temperatures, glowing with intense radiation. But the black hole does not quietly consume its meal. It unleashes a storm of energy through powerful winds and relativistic jets, blasting outward into the heart of the galaxy. This outburst is the black hole's way of regulating its own growth and the growth of its galactic home. The energy from these outflows heats the vast reservoirs of cold, dense gas that would otherwise collapse to form new stars. Think of a pot of water on a stove. If you turn the heat up high enough, the water will boil and turn to steam, never settling into a calm state. The black hole's feedback acts like that intense heat, keeping the galactic gas too hot and turbulent to condense into the nurseries required for new stars. This creates a delicate cosmic balance. A burst of star formation sends more gas swirling toward the center, feeding the black hole. The black hole then responds with a powerful outburst that shuts down the star formation across the galaxy, effectively turning off its own fuel supply. This cycle of feast and famine explains the fate of massive elliptical galaxies. They are the red and dead retirement homes of the universe, their star-forming gas kept perpetually hot by the occasional but powerful temper tantrums of the central black hole. Without this self-regulating feedback, these galaxies would have long ago exhausted their gas in a frenzy of star birth, or perhaps collapsed into something entirely different. The monster at the center is not just a destroyer of stars, it is a galactic governor, its fierce energy shaping the very life and death of its stellar city. The timeline for building a cosmic giant seems impossibly short. We now find quasars, the brilliant beacons powered by voracious supermassive black holes, shining from the universe's infancy. These quasars existed when the cosmos was less than 1 billion years old, a mere toddler in cosmic terms. The sheer existence of these objects presents a monumental puzzle. How did black holes grow to billions of solar masses in what amounts to the blink of a cosmic eye? The standard model of slow, steady growth through accretion faces a severe challenge here. A black hole seed from a first-generation star would have to feed at its maximum possible rate, non-stop, for hundreds of millions of years to reach the masses we observe. It is like trying to grow a giant sequoia tree overnight from a single seed. The math simply does not add up, forcing astronomers to consider more exotic and rapid formation scenarios. Perhaps the seeds themselves were born giants, in the dense, pristine gas of the early universe before heavy elements existed to cool the gas and allow it to fragment into normal stars. Vast clouds could have collapsed directly under their own weight. This direct collapse would skip the star formation stage entirely, creating a black hole seed with a mass of tens of thousands of suns right from the start. This massive head start would allow it to gorge on the surrounding gas and rapidly balloon into the supermassive quasars we see. Another possibility involves a frantic, chaotic environment in the first galaxies. A dense cluster of early stars could have collided and merged, their stellar mass black holes coalescing into a single, much larger object very quickly. This bottom-up build-up happening in a crowded nuclear star cluster could provide the rapid growth spurt needed. The light from these ancient quasars is therefore a message from a more violent, extreme era of the cosmos, an era where the rules of building giants were fundamentally different from the slower, more orderly universe we see today. This cosmic censorship, the idea that nature hides its most bizarre creations, leads us to a theoretical monster even stranger than a black hole. What if the event horizon simply vanished? The result would be a naked singularity, a point of infinite density exposed for the entire universe to see. Without the protective shroud of an event horizon, the raw, unfiltered singularity would lie bare, its gravitational madness on full display. The laws of physics as we know them would break down at its surface. Causality, the rule that cause must always come before effect, could become meaningless. Predictability would vanish from the universe. For this reason, most physicists cling to the cosmic censorship hypothesis, a profound belief that nature abhors such a paradox. It proposes that general relativity always conspires to protect the universe from its own worst excesses. Any collapsing star or spinning object will always form an event horizon to cloak the singularity, hiding its infinite weirdness from the rest of reality. A naked singularity is considered so disruptive to the logical order of the cosmos that it is deemed impossible. The mathematics, however, can be tantalizing. One hypothetical path to this state involves a black hole spinning at the absolute maximum possible rate. If it could be spun up just a little bit more, the equations suggest the event horizon could shrink to a point and disappear like a soap bubble popping, leaving the singularity naked. Another possibility is if a black hole could somehow lose all of its mass to Hawking radiation. Perhaps the final evaporation would leave a tiny, exposed knot of spacetime. Yet the consensus is that some quantum effect we do not yet understand, would always step in to prevent this cosmic undressing. The universe, it seems, prefers to keep its deepest secrets veiled in darkness, protecting the smooth, predictable reality outside from the infinite chaos lurking within. The silent darkness of a black hole can scream its existence across 1 billion light years. This scream is not a sound, but a vibration in the cosmos itself, a ripple in space-time known as a gravitational wave. When two black holes spiral toward their final, violent merger, they churn the fabric of reality, sending out these tremors at the speed of light. For decades, these waves were only a theoretical prediction of Einstein's genius, but in 2015, humanity heard them for the first time. The key was an instrument of almost impossible sensitivity, the Laser Interferometer Gravitational Wave Observatory, or LIGO. It does not listen with microphones, but with laser light traveling down 2.5-mile long arms arranged in an L shape. A passing gravitational wave, weaker than the tiniest subatomic particle, momentarily stretches one arm while squeezing the other. This minuscule change, smaller than the width of a proton, alters the laser light's journey just enough to create a detectable signal. The first sound they ever heard was the signature of two stellar mass black holes, each about 30 times the mass of our Sun, colliding in a galaxy far away. The signal was a rapid increase in frequency and amplitude, a cosmic chirp that lasted only a fraction of a second. In that brief blip was the energy of 3 entire suns converted directly into pure gravitational waves, a testament to the sheer violence of the event. This chirp was the proof, the direct observation of black holes and the waves they create. But LIGO is only sensitive to the high-frequency chirps of these smaller black holes. To hear the true titans, the supermassive black holes at galactic centers, we need to listen for a much deeper sound. The merger of billion solar mass giants would not create a chirp, but a low-frequency boom, a cosmic thunder that rumbles for years or even decades. Our current detectors are deaf to this profound bass note of the universe. The future of this new sense lies in space itself. A planned mission called the Laser Interferometer Space Antenna, or LISA, will consist of 3 spacecraft flying in a perfect triangle millions of miles apart, connected by laser beams. In the pristine quiet of space, free from Earth's seismic rumble, this colossal instrument will finally tune into the low-frequency gravitational wave background. It will hear the chorus of supermassive black hole mergers happening all across the universe, the slow, stately dances that built the galactic giants we see today. This will open an entirely new window onto the cosmos, allowing us to hear the foundational events that shape the large-scale structure of everything we see. The profound silence of a black hole is an illusion. Even in its perfect darkness, a faint whisper of quantum activity is always present. This quiet sizzle at the edge of reality holds the key to their ultimate fate, a secret that rewrites their story from eternal to ephemeral. They might not be forever. The mechanism for this cosmic decay is Hawking radiation, a process that connects the vast scales of gravity to the ghostly rules of the quantum world. At the event horizon, where gravity is supreme, the vacuum of space is not truly empty. It is a seething sea of virtual particles, pairs of matter and antimatter that constantly flicker into and out of existence, borrowing energy from the universe for a fleeting moment before annihilating each other and paying the debt back. Normally, this dance happens too quickly for us to notice, but at the precipice of a black hole, the immense gravitational field can tear these pairs apart. In a quantum robbery, one particle falls across the event horizon, lost forever. Its partner, however, is gifted with real energy and flies away into space as genuine radiation. From the perspective of an outside observer, the black hole has just emitted a particle, but there is a profound cost. The energy for this creation was stolen from the black hole's own gravitational field. To conserve energy, the black hole must lose a tiny, corresponding amount of mass. This is an excruciatingly slow leak. For a supermassive black hole with the mass of millions of suns, the rate of evaporation is so infinitesimal that it loses far more mass from the cosmic microwave background radiation it absorbs than it loses from Hawking radiation. It is essentially immortal on any timescale we can comprehend. But in a far, far future, when the universe has expanded and cooled to near absolute zero, the slow bleed will finally begin to dominate. As the black hole loses mass, its event horizon slowly shrinks, which in turn increases the temperature of the radiation it emits. This creates a runaway process. The smaller it gets, the hotter it glows, and the faster it evaporates. The final moments are not a quiet fade. When the black hole's mass becomes minuscule, it unleashes its remaining energy in an immense final burst of radiation, a flash of light and particles that signals the end of a cosmic era. The timeline for this is almost beyond human imagination. A black hole with the mass of our Sun would take 10 to the 67 years to evaporate, a number so vast it has more digits than there are atoms in our galaxy. For a supermassive black hole, the wait is trillions of times longer. Their reign is measured not in billions of years, but in googolls of years, a timescale where even the protons that make up atoms may have decayed into nothingness. In the very end, every anchor, every giant, every cosmic gatekeeper may vanish in a final, brilliant flash, leaving behind only a faint echo of their gravitational memory in an otherwise silent and dark universe. This magnetic personality is not a gentle force. Within the frantic whirlpool of the accretion disk, superheated gas is ionized, meaning its atoms are ripped apart into a seething soup of charged particles, primarily electrons and protons. As this plasma churns at nearly the speed of light, these charged particles create immensely powerful electrical currents, and where you have moving charges, you generate magnetic fields. The disk becomes a self-exciting dynamo, winding these magnetic field lines into braids of unbelievable power and tension. These fields are not passive observers. They act as a cosmic puppet master, controlling the very flow of the feast. The magnetic field lines become tangled within the disk, creating a powerful magnetic friction that helps to slow the orbital motion of the inner material, allowing it to lose energy and spiral inward toward its doom. Without this magnetic braking, matter would have a much harder time crossing the final distance into the black hole's grasp. But the most spectacular role of these magnetic fields is in launching the relativistic jets. The black hole's own rotation, its spin, is a colossal reservoir of energy. The wound-up magnetic field lines act as a direct conduit to tap into this power. They function like the rigid arms of a gigantic slingshot, anchored in the inner accretion disk and the black hole's ergosphere. Some of the inflowing plasma is caught by these field lines and accelerated outward, not in a wide wind, but focused into two narrow, oppositely directed beams along the black hole's rotational axis. This is the only direction free of the disk's dense material, a clear path for escape. The process is so efficient that it can convert the raw rotational energy of the black hole itself into the directed kinetic energy of the jet, a testament to magnetic fields acting as the universe's ultimate power transmission cables. That magnetic power to accelerate matter to near light speed pales before an even grander act of cosmic alchemy. The 26th secret reveals that supermassive black holes are indirectly responsible for forging the universe's most precious treasures, including gold. The story begins not within the black hole itself, but in the dense stellar neighborhoods it governs. The incredible gravitational pull at a galactic center packs stars together in a frantic, high-speed dance. In this chaotic environment, binary pairs of neutron stars, the ultra-dense corpses of massive stars, can form and orbit each other for eons. Their fate is sealed by the black hole's overarching influence. The subtle gravitational nudges from the central giant can destabilize the orbits of these neutron star pairs over millions of years, slowly tightening their spiral until they are destined to collide. When two neutron stars finally merge, the event is one of the most cataclysmic and productive in the cosmos. The collision is so violent and releases so much energy that it briefly becomes the site of a runaway nuclear furnace. In a process known as rapid neutron capture, or the R process, a flood of neutrons inundates atomic nuclei. Seed nuclei, like iron, rapidly gobble up these free neutrons, building themselves into heavier and heavier elements in an instant. This is the cosmic forge where the heaviest elements in the periodic table are born, including gold, platinum, and uranium. The evidence for this spectacular origin story was confirmed in 2017. Astronomers observed a neutron-star merger both through gravitational waves and its brilliant light. The aftermath of the collision glowed with the distinctive signature of newly synthesized heavy elements, a cloud of cosmic debris shining with the light of forged gold. So, while the black hole never touches the material, it acts as the ultimate puppeteer. Its gravity sets the stage for the collision, triggering the event that scatters these newly minted heavy elements across the galaxy. Every gold ring on Earth contains atoms that were likely born in the furious aftermath of a neutron star merger, a merger that may have been set in motion by the silent, gravitational hand of a supermassive black hole at the heart of a long-vanished galaxy. That shadow, a perfect circle of darkness against a brilliant ring of fire, is not the event horizon itself. It is something even more profound, a silhouette cast by the black hole's gravity against the backdrop of its own glowing accretion disk. This dark central region is the black hole's shadow, a void created because the gravitational pull is so overwhelming that it captures the very light emitted from the disk behind it. The bright ring surrounding it is the ultimate demonstration of gravitational lensing, light from the far side of the accretion disk being bent around the cosmic pit in a perfect, luminous halo. This single image, a triumph of global cooperation, confirmed our theories with stunning clarity. The size of that shadow is a direct measuring stick for the black hole's mass. The diameter of the dark region matched the predictions for an object weighing 6.5 billion times the mass of our Sun, a perfect fit for the monster at the heart of Messier 87. The shape of the shadow also holds clues about the black hole's spin. A non-spinning black hole would cast a perfectly circular shadow, but a spinning one, dragging spacetime around with it, should create a shadow that is slightly flattened or asymmetrical. While the first image was consistent with a circular shadow, future, sharper images from the Event Horizon Telescope will look for this telltale distortion, allowing us to measure the spin of this distant giant directly. This was not just a picture, it was a fundamental test of Einstein's general relativity in the most extreme environment imaginable, and his equations passed with flying colors. The void, for the first time, had a face, and it looked exactly as science had foretold. That final flash of Hawking radiation signals not an end but a transformation. After an almost eternal existence, the black hole has evaporated down to a scale so small it defies all known physics. The 28th secret suggests the black hole does not simply vanish into nothingness. It may leave behind a ghost, a stable relic known as a Planck mass remnant. This theoretical object would be unimaginably tiny, with a size on the scale of the Planck length, a unit so small that a single atom is vast in comparison. Yet it would still contain the mass of a small mountain, compressed into a volume smaller than any subatomic particle. This is the ultimate density, a frozen cinder of a once great cosmic giant. The existence of such a remnant is a potential solution to the information paradox. Instead of the information about everything that ever fell into the black hole being lost forever in the final evaporation flash, it could be preserved, locked away within this stable, indestructible knot of spacetime. This tiny object would be a perfect, permanent vault, holding the complete history of the black hole's past, but we could never hope to open it. Its gravitational pull would still be immense for its size, and its surface would be a zone where the laws of quantum gravity reign supreme. This makes the remnant far more than just a cosmic footnote. It would be a direct physical window into the theory of quantum gravity, the long-sought unification of general relativity and quantum mechanics. Studying such an object, if we could ever find one, would reveal the true fabric of reality at its smallest scales. It represents the final state of matter, a silent, stable, and eternal testament to the universe's most powerful objects, a diamond forged in the fire of a black hole's death. The anchors of galaxies are not isolated monarchs. They are linked by a hidden architecture, a cosmic web of dark matter that spans the entire observable universe. This vast structure, a network of immense filaments and dense nodes, does more than just outline where galaxies will form. It acts as a cosmic highway system, directing rivers of primordial gas toward the waiting supermassive black holes at the centers of those galaxies. The black hole's growth is therefore not just a local affair. Its fate is tied to the largest structures in existence. When a galaxy lies at the intersection of two or more of these dark matter filaments, it receives a continuous, rich supply of cold gas, a feast delivered directly to its doorstep. This steady influx can keep the central black hole in a near-constant state of activity, powering brilliant quasars for billions of years. The black hole becomes a bright node in the web, its brilliance dictated by its privileged position in the cosmic geography. This explains why we find the most massive and active black holes in the densest clusters of galaxies, the very knots where the web's filaments converge. They are the ultimate beneficiaries of a universal delivery service, their growth supercharged by the invisible flow of dark matter that guides the building blocks of reality itself. This ultimate simplification of reality into a few numbers creates a paradox so deep it shakes the foundations of physics itself. The 30th secret is that black holes exist at a boundary, a frontier where our two most successful theories of reality utterly fail to communicate. On one side stands Einstein's general relativity, a masterpiece that describes gravity as the elegant warping of spacetime on cosmic scales. Its equations perfectly predict the orbits of planets, the bending of starlight, and the very existence of black holes. On the other side sits quantum mechanics, the wildly successful rulebook for the subatomic world, governing the bizarre behavior of particles and forces. Both theories are spectacularly accurate within their own domains, but they speak different languages. At the heart of a black hole, where an entire star's mass is crushed into an infinitely dense point, the singularity, both theories are needed simultaneously. General relativity demands the singularity exists, a point of infinite density where space-time curvature becomes infinite and its own laws break down. But quantum mechanics insists that such a thing is impossible, that infinities do not appear in nature, and that information can never be truly lost. The event horizon is the battleground where this conflict becomes unavoidable. It is the precise location where the immense, smooth gravity of general relativity meets the frantic, probabilistic uncertainty of the quantum vacuum, giving rise to phenomena like Hawking radiation. To understand what truly happens at the singularity or at the event horizon, we require a single, unified theory that can marry the vast with the vanishingly small. This holy grail of physics is known as quantum gravity. It is the missing framework that would describe how gravity works at the Planck scale, the absolute smallest possible size in the universe. Think of it like this: we have a perfect map for navigating continents, general relativity, and a perfect blueprint for building a single house, quantum mechanics. But we have no idea how to connect the two. A black hole is like a city that appears on the continental map, but when you arrive, you find it's built from materials and with rules that our house blueprint cannot explain. Solving this puzzle means rewriting our understanding of reality from the ground up. The quest for quantum gravity is not just an academic exercise, it is a journey to answer the most fundamental questions about our cosmos. What is spacetime made of at its smallest level? What truly happens at the center of a black hole? The existence of these cosmic monsters is a constant, gravitational reminder that our picture of the universe is still incomplete, and that the final secret may be a new set of laws waiting to be discovered. The bizarre quantum world does not end at the event horizon. It may clothe the entire black hole in a ghostly atmosphere. picture a single atom with electrons buzzing in fuzzy clouds around a dense nucleus. Now replace the nucleus with a black hole and the electrons with a swarm of ultralight theoretical particles like actions. This is the concept of a gravitational atom, a black hole enveloped in a vast, invisible quantum cloud. These hypothetical particles, drawn by the black hole's immense gravity, would not fall in. Instead, they could settle into stable, standing waves, forming bound states that orbit the silent giant. This cloud would be enormous, potentially spanning a distance far greater than our entire solar system. Yet it would be utterly invisible, a ghostly halo detectable only through its subtle gravitational influence. The true magic happens when two of these gravitational atoms spiral together. As they merge, their respective clouds interact, sloshing and interfering with each other in a complex quantum dance. This interaction imprints a unique, oscillating signature onto the gravitational waves emitted during the collision. Instead of a clean chirp, the signal would carry a distinct wobble or beat, a fingerprint of the underlying quantum structure. Detecting this signal would be like hearing the subtle harmonies in a cosmic chord, revealing the presence of the invisible cloud. Finding this signature would be a monumental discovery. It would provide the first direct evidence for these mysterious ultralight particles, candidates for the dark matter that permeates the universe. More profoundly, it would open a completely new window into quantum gravity, allowing us to probe how the fuzzy rules of the quantum realm manifest on the colossal scale of a black hole. The silent, simple giant of the no-hair theorem might be hiding a secret quantum complexity after all, its gravitational waves carrying the faint whisper of a ghostly atmosphere. The smooth, featureless void predicted by general relativity might be a cosmic illusion. According to the radical fuzzball proposal from string theory, there is no singularity at all. The interior of a black hole is not a place of infinite density where the laws of physics break down. Instead, it is filled with a dense, vibrating, and fantastically complex ball of strings. These are the fundamental threads of reality proposed by string theory, tiny loops and strands vibrating at specific frequencies to create every particle and force in the universe. In this view, when matter falls into a black hole, it does not get crushed into a single point. It gets transformed, its information woven into the intricate, tangled tapestry of this cosmic fuzzball. The entire volume inside the event horizon becomes a giant, pulsating knot of stringy energy with no sharp boundary or central singularity. This has a breathtaking implication for the information paradox. Information is never truly lost. It is merely scrambled and stored within the complex quantum state of the fuzzball, preserved forever in the vibrating strings. There is no destruction, only a transformation so profound that from the outside it appears as simple mass and spin. Think of the difference between a single, featureless marble and a ball of a billion intertwined rubber bands. The marble is simple and smooth, defined by one number, its diameter. The ball of rubber bands is a mess of loops and knots, each one holding a memory of how it was tangled. The fuzzball is the ultimate ball of rubber bands, its internal complexity preserving the history of everything it has ever absorbed. While this remains a highly theoretical idea, it offers a beautiful and elegant solution to the most vexing problems of black hole physics, suggesting that the true nature of the void is not emptiness, but the most complex object in the entire cosmos. Our own galactic center holds a secret of profound silence. Sagittarius, a star, a monster 4 million times the mass of our sun, slumbers in a deep and puzzling quiet. This quiescence is its current state, a stark contrast to the brilliant, active quasars seen in other galaxies. The reason for this dormancy lies in a simple yet cosmic reality. The black hole is starving. The immediate environment around Sagittarius, a star, is a relative desert, a region largely cleared of the dense, cold gas clouds that would otherwise serve as its primary fuel. This scarcity is not a natural or permanent condition. It is likely the consequence of the black hole's own violent history. In the distant past, Sagittarius, a star, was almost certainly an active quasar, feeding voraciously and unleashing powerful outbursts of energy. Those past eruptions would have acted like a cosmic broom, sweeping its immediate vicinity clean. The intense radiation and ferocious winds from its active phase would have heated, dispersed, or blown away the surrounding gas and dust, pushing the nourishing material far beyond its easy reach. Without a steady stream of fresh fuel falling into its accretion disk, the black hole has entered a period of deep hibernation, its immense power latent and waiting. Even its occasional hiccups, like flaring from a passing cloud of gas or the tidal disruption of a stray star, are brief and faint compared to the brilliant beacons it could power. This quiet phase is a temporary chapter in a long and dynamic life, a period of cosmic peace enforced by the black hole's own past ferocity. Their silence is a prelude to a cosmic roar. A single, hidden engine can generate a brilliance so intense it drowns out the combined light of every star in its galaxy. This is the secret of the quasar, the most powerful and persistent beacon in the universe. At its heart lies a supermassive black hole in a state of extreme gluttony, feasting on a continuous, massive influx of gas and dust. This material does not fall in quietly. It forms an accretion disk of staggering proportions, a whirlpool of matter heated to incandescent fury by friction and gravitational forces. The energy released in this frantic process is almost beyond comprehension. A single quasar can shine with the luminosity of 1 trillion suns, outshining its entire host galaxy so completely that from a distance we often see only the brilliant, star-like point of light at its core. The name itself means quasi-stellar radio source, a label born from their initial mystery when they appeared as strange, star-like objects emitting powerful radio waves. We now know they are not stars at all. They are the visible signature of a black hole's ultimate feeding frenzy, a testament to the raw power locked within gravitational collapse. Their incredible distance is another key to their mystery. The light from the most distant quasars has been traveling for over 13 billion years to reach us, meaning we are seeing them as they were when the universe was in its raw, formative youth. Their existence tells us that supermassive black holes were not only present in the early cosmos, but they were already achieving staggering masses and dominating their environments with an energy output that shaped the evolution of the first galaxies. A quasar is a black hole shouting its presence across the void, a lighthouse whose beam cuts through cosmic time to illuminate an era of violent, brilliant growth. The cosmic family of black holes has a puzzling gap. We know the stellar mass ones born from dying stars and the supermassive giants that rule galactic centers. But what about the middle children? The hunt for intermediate mass black holes is a search for a missing evolutionary link. These would be the cosmic stepping stones, with masses ranging from a few hundred to a few 100,000 times that of our Sun. They are the theoretical seeds, the crucial middle stage that explains how a stellar corpse could balloon into a galactic titan. Finding them has proven incredibly difficult. They are too massive to form from a single collapsing star, yet not massive enough to dominate a bright galactic core and announce their presence with brilliant quasars. They are the cosmic ghost hiding in plain sight. One of the most promising places to look is within the dense, ancient clusters of stars known as globular clusters. These spherical swarms, orbiting the outskirts of galaxies like our own Milky Way, contain millions of stars packed into a relatively small volume. In such a crowded environment, stellar mass black holes could collide and merge over time, building themselves up into an intermediate mass object. We search for their gravitational signature by watching the motions of stars at the very heart of these clusters. If the stars are whipping around an invisible, central point at surprising speeds, it points to a hidden anchor of significant mass. Another clue comes from the strange, off-center flickers of intense radiation. In 2019, astronomers witnessed a spectacular event, a tidal disruption flare from a source in a distant galaxy. The pattern of the light suggested the star was shredded not by a supermassive black hole, but by an object of intermediate mass, a rare and precious sighting of a middleweight monster at its gruesome work. Their existence is vital to our origin story for the supermassive giants. A stellar mass black hole seed would take too long to grow, but an intermediate mass seed, a ready-made heavyweight born from the chaos of dense clusters or the direct collapse of primordial gas, could gorge itself efficiently in the early universe, rapidly reaching supermassive status. Finding these missing links would complete the family portrait, showing us the crucial adolescent phase in the life of a cosmic giant. The silent evaporation of a black hole presents an elegant solution, but it resurrects the ghost of the information paradox. If the black hole vanishes, leaving only a faint, random spray of Hawking radiation, then all the intricate details about every star and atom that ever fell in would be erased from the universe. This is a violation of a sacred rule in quantum mechanics, the principle that information must never be destroyed. For decades, this paradox seemed intractable, a fundamental contradiction at the heart of physics. But a new idea is emerging from the frontier of theoretical research, one that suggests black holes can, in a strange way, remember. This is not a memory like our own, a collection of conscious thoughts. It is a memory etched into the fabric of the radiation itself. The key lies in the concept of entanglement, a bizarre quantum connection where particles can share a fate no matter how far apart they are. In the Hawking radiation process, the particle that falls in and the particle that escapes are deeply entangled. The recent island conjecture proposes a breathtaking resolution. It suggests that as the black hole evaporates, secret regions within its gravitational field, called quantum extremal surfaces or islands, become subtly connected to the escaping radiation. Information about what fell into the black hole is not trapped inside the vanishing core. Instead, it is transferred and imprinted onto the radiation through these complex, non-local quantum correlations. The radiation is not random. It is a scrambled but perfect record of the black hole's entire history. Decoding this record from the outside is like trying to read a book that has been put through a shredder and its pages scattered to the wind. In principle, however, the information is there, preserved forever in the intricate quantum links between the emitted particles. This subtle remembering challenges our most basic notions of locality and reality, hinting that the true nature of a black hole is not a simple pit, but a deeply interconnected quantum system whose secrets are slowly being teased out by the very radiation that signals its end. This invisible influence might extend beyond the matter we can see. The 37th secret asks if dark matter itself is part of the black hole's hidden diet. We know dark matter vastly outweighs normal matter, forming vast, invisible halos around every galaxy. Its gravitational pull is the primary reason galaxies hold their shape. So it is natural to wonder, does this mysterious substance also fall into the supermassive black hole at the center? Theoretically, yes. Dark matter particles should be affected by gravity, just like everything else. They would orbit the galactic center, and some of their paths would inevitably cross the event horizon, never to return. This would provide a slow, steady trickle of mass, a background hum of accretion from the unseen universe. Yet this process is incredibly inefficient. Dark matter, by its very nature, rarely interacts with itself or normal matter. It does not form a dense, clumpy accretion disk that can lose energy and spiral inward easily. Most dark matter particles would simply whip around the black hole on wide, looping orbits, like comets on a perpetual journey around the sun, only rarely coming close enough to be captured. This makes dark matter accretion a very poor food source for a growing giant. It could never power a brilliant quasar or explain rapid growth, but what if dark matter offers a different kind of sustenance? Some theories suggest that certain types of dark matter particles are their own antimatter counterparts. If two such particles collided, they would annihilate each other in a flash of pure energy, much like matter and antimatter. If this annihilation occurred near the black hole, could that released energy be harnessed? Imagine a faint, continuous glow of energy emanating from the darkness, not from swallowed stars, but from the self-destruction of the invisible halo surrounding it. This energy could potentially heat the surrounding gas, subtly influencing the black hole's feeding habits, or even providing a steady, low-level power source during its long dormant phases. While these ideas remain in the realm of compelling speculation, they highlight a profound truth. The supermassive black hole is not just an anchor for the visible galaxy. It is a gravitational knot tied into the very fabric of the dark universe, a place where the known and the unknown meet. Its growth and behavior may be dictated by forces we are only beginning to sense, a silent conversation with the cosmos's deepest secret. That brilliant ring of fire surrounding the void is a cosmic lie. The accretion disk is not a serene, orderly whirlpool. It is a perpetual hurricane of incandescent gas, a battlefield of competing forces where matter screams its final moments in a storm of light. The turbulence begins with simple friction. As layers of gas spiral inward at different speeds, they grind against each other, creating immense heat. But this is just the start of the chaos. The entire disk is prone to violent instabilities, where sections can suddenly break into waves or clump together, collapsing under their own gravity before being torn apart again by tidal forces. This constant churning creates shock waves that reverberate through the plasma, compressing and heating it to even more extreme temperatures in sudden, brilliant flashes. Yet the true architects of this storm are the magnetic fields. Wound into impossibly tight coils by the disk's frantic rotation, these fields become stores of titanic energy. They can snap and reconnect in colossal magnetic explosions, events far more powerful than any solar flare. These reconnection events act like particle slingshots, accelerating electrons to near light speed. When these ultra-relativistic particles are whipped through the magnetic fields, they emit a torrent of high-energy radiation, from X-rays to gamma rays. This is the primary source of the brilliant glow we see, born not from calm heat, but from continuous magnetic lightning strikes within the storm. The disk we observe as a smooth, luminous halo is in reality a maelstrom of superheated chaos, its beautiful light the direct result of the most violent weather in the universe. The relentless chaos of the accretion disk finds a strange, theoretical opposite in the silent perfection of a white hole. This 39th secret is one of pure speculation, a cosmic idea born from the symmetrical beauty of mathematics. A white hole is the exact temporal reverse of a black hole. Where a black hole's event horizon is a one-way street leading only inward, a white hole's boundary would permit only exit. Nothing could ever cross from the outside in. It would be a cosmic fountain, eternally spewing out matter and energy from a source hidden forever beyond its own impenetrable barrier. The equations of general relativity allow for such an object, but they offer no clue as to how one could ever naturally form. It is a solution that seems physically impossible in our universe, a place where entropy and the forward arrow of time seem to demand that gravity only pulls things together, never pushes them apart for eternity. Yet this theoretical oddity leads to a breathtaking possibility. If a black hole is a tunnel through spacetime, a wormhole, then its other end would logically be a white hole. Everything that falls into the black hole entrance would be violently expelled from the white hole exit, perhaps into another universe or a different region of our own. This offers an elegant, though unproven, solution to the information paradox. Information is not destroyed, it is simply relocated, fired out of this cosmic cannon into a new reality. The most profound application of this idea connects it to the very beginning of everything. Some cosmologists have proposed that the Big Bang itself possesses the key characteristics of a white hole. It was a singular event from which all matter and energy erupted, a point of genesis that was, from our perspective, impossible to enter from the outside. Our entire observable universe could be the ongoing output of a primordial white hole, a single, colossal eruption of spacetime that set the cosmic clock ticking. In this view, the supermassive black holes at galactic centers are not just anchors, but perhaps echoes of that first great explosion, their hidden interiors still connected to the moment of creation through a physics we have yet to understand. The silent, rhythmic orbits of stars around our galactic center are more than just a celestial dance. They are the ticking hands of a cosmic clock, one that tests the very laws of physics with every passing year. The 40th secret reveals that supermassive black holes serve as the universe's most precise laboratories, allowing us to probe the limits of Einstein's theory of gravity in ways no Earth-bound experiment ever could. At the heart of this effort is a star known as S2. This star does not take millions of years to complete its orbit. It makes a full, frantic lap around Sagittarius, a star, in just 16 years, whipping around at speeds exceeding 3 million miles per hour at its closest approach. That point of closest approach, called the periaps, is where the magic happens. As S2 screams through the black hole's intense gravitational field, its path is not a perfect static ellipse. The orbit itself rotates, a subtle effect known as Schwarzschild precession. It is as if the hands of a clock were slowly shifting around the dial with each tick. General relativity predicts the exact amount of this precession with stunning precision. For years, astronomers have tracked S2, meticulously mapping its path against the background of more distant stars. The result, the star's orbit precesses exactly as Einstein foretold, a beautiful confirmation of his century-old theory in the most extreme environment we can observe. But the search is not over. The real excitement lies in the hunt for a tiny, unexpected deviation. What if, on its next close pass, S2's orbit precesses just a fraction of a percent more or less than predicted? Such a minute discrepancy would be a scientific earthquake. It would be a crack in the flawless facade of general relativity, a signal that a new, deeper theory of gravity is needed to explain the universe's most powerful forces. This could point the way towards quantum gravity or reveal the influence of hidden dimensions. Every precise measurement of a star's dance around the void is another tick of this cosmic clock, counting down to a potential revolution in our understanding of reality itself. Light itself becomes a prisoner just outside the abyss. This region is known as the photon sphere, a ghostly shell of trapped reality where gravity bends the fabric of space into a perfect circle. It is not a physical surface you could stand on, but a mathematical boundary, a point of no escape for light. Here, the gravitational pull is so perfectly tuned that photons, the particles of light, are forced into unstable circular orbits. They do not spiral in and they do not fly away. They skim the edge of eternity, tracing a perfect ring around the central darkness. This delicate balance is a cosmic tightrope. The smallest perturbation, the faintest nudge, will send these captive photons careening. One slight push inward, and the photon finally loses its billion-year struggle and plunges across the event horizon, lost forever. One slight push outward, and it escapes the black hole's clutches, flying free into the universe to perhaps eventually be seen by a distant telescope. This shell of trapped light is the primary reason we see the black hole's shadow. The dark center in images like the one of Messier 87 is not just the event horizon. It is a void magnified by this photon sphere, which captures and redirects the light from the far side of the accretion disk, creating that brilliant, lensed ring of fire around a perfect circle of blackness. For a hypothetical observer daring enough to float near this boundary, the visual effects would be a dizzying paradox. You could look to the side and see the back of your own head. Light emitted from your helmet would travel all the way around the black hole in that circular orbit and enter your own eyes. the entire universe would be compressed into a thin, blinding band of light wrapped around a sphere of absolute black, a final, maddening carnival mirror before the universe winked out completely. A planet orbiting a black hole would witness a sun that never rises. Its sky would be dominated by a perfect circle of blackness, encircled by a permanent, searingly bright ring of fire. This is the light from the accretion disk, a whirlpool of superheated matter that could provide the energy for a world we can barely imagine. The planet would need to orbit at a very specific, safe distance, far from the event horizon where tidal forces would tear it apart. In this stable orbit, the black hole itself would be a cold, dark presence, but the sky would be bathed in the relentless, reflected light of the doomed material swirling around it. This eternal, directionless twilight could serve as a substitute for a star. Photosynthetic life, if it could evolve, might harness this brilliant, ambient light, much like deep-sea organisms on Earth use the faint glow of thermal vents. But there is another, far stranger possibility. What if the black hole were small? A stellar mass black hole left over from a dead star emits Hawking radiation. For a large black hole, this radiation is fantastically weak and cold. But as a black hole loses mass and shrinks, its Hawking radiation grows hotter and more intense. A small, mountain-sized black hole would glow with a temperature of millions of degrees, emitting a ferocious blast of X-rays and gamma rays. A planet orbiting at a safe distance from such a tiny, sizzling monster would be warmed by this hellish glow. The energy source would not be the gentle light of a star, but the death throes of a primordial relic. Life here would be unlike anything we know, forced to shelter from the lethal radiation, perhaps deep underground or beneath a global ocean, harnessing the geothermal heat generated by the constant bombardment. This is, of course, the most extreme speculation. The stability of such a system is questionable, and the origins of such a planet are a mystery in themselves. Yet the mere possibility forces us to expand our definition of a habitable zone. Life may not be confined to the golden warmth of stars. It could cling to the precipice of the ultimate cold, drawing energy from the faint quantum whisper of a dying black hole or the brilliant funeral pyre of an accretion disk, a testament to life's potential to find a way in even the most hostile corners of the cosmos. That perfect, serene darkness of the event horizon is an illusion. At the very precipice of the void, reality itself is never still. The 43rd secret reveals a quantum tremor, a constant microscopic fizz at the foundation of existence. This is the realm of spacetime foam. Picture the surface of the ocean on a perfectly calm day. From a distance, it appears as smooth as glass, but if you could shrink down to the size of a single atom, you would see a frantic, churning chaos. The water would be a seething dance of molecules, constantly colliding and vibrating. Space-time itself behaves in a similar way. According to the principles of quantum mechanics, empty space is not truly empty. At scales a trillion times smaller than an atom, it is a bubbling, turbulent foam. Tiny wormholes and baby universes are thought to flicker in and out of existence in a frantic, probabilistic dance. These are the quantum jitters, the fundamental uncertainty of reality made manifest. Now, place this quantum foam at the edge of a supermassive black hole's event horizon. The immense gravitational field amplifies and stretches these effects. The gentle, universal fizz becomes a violent, microscopic storm. Here, the very concepts of before and after can break down. The smooth, predictable geometry of Einstein's general relativity collides with the chaotic, probabilistic rules of the quantum world. This foaminess is not something we can ever see directly, but it is a necessary prediction of any theory that tries to unite gravity with quantum mechanics. It is the ultimate texture of reality, a reminder that beneath the seemingly solid stage upon which planets and stars move, there is a frenetic, ever-changing quantum sea, churning most violently at the brink of the ultimate abyss. This silent, precise clockwork of stellar orbits can be violently shattered. The merger of two supermassive black holes, a cosmic event of unimaginable power, does not always result in a peaceful new anchor at the galactic center. The gravitational waves that carry away the energy of this collision are not always emitted evenly in all directions. If the two black holes are of different masses or are spinning at different rates and angles, the final blast of gravitational radiation can shoot out like a cannon from one preferred direction. For every action, there is an equal and opposite reaction. The newborn black hole recoils from this asymmetric blast, kicked away at a staggering velocity. We are not talking about a gentle nudge. These recoil kicks can propel the black hole at speeds exceeding 5,000 kilometers per second, fast enough to overcome the gravitational pull of even the largest galaxies. The result is a rogue black hole, a cosmic monster cast out from its own city, doomed to wander the intergalactic void forever. Picture a king moments after his coronation, violently thrown from his throne and launched into the wilderness beyond the city walls. This is the fate of these kicked black holes. They take nothing with them, leaving their entire galactic domain behind. For the galaxy that loses its central anchor, the consequences are profound and strange. The stars at the very core, once held in a tight dance by the black hole's gravity, would slowly relax into a new, more disordered configuration. The regulation of star formation, once governed by the black hole's feedback, would cease. The galaxy might experience a new, unregulated burst of stellar birth, a final flowering before its eventual decline. Spotting these rogue giants is one of astronomy's great challenges. They are invisible, solitary, and moving through the empty darkness between galaxies. Our only hope of finding them is if they are actively feeding, pulling in wisps of intergalactic gas as they travel. A single, brilliant point of light moving at an impossible speed against the backdrop of distant galaxy clusters would be the telltale sign of a king in exile, a ghost from a galactic collision that happened billions of years ago. This holographic principle turns our intuition about reality inside out. It proposes that our perception of a three-dimensional world with its depth and volume might be a magnificent illusion. The true description of everything within a given space, including every atom, every force, and every event, could be entirely encoded on a two-dimensional surface that surrounds it like a cosmic film projector. For a black hole, this surface is its event horizon. The mind-bending implication is that the three-dimensional interior we imagine, with its crushing singularity and lost information, is not the primary reality. It is a holographic projection, an emergent phenomenon generated from the complex quantum data stored on the two-dimensional boundary. You, your memories, the world around you, all of it might be akin to a shimmering hologram, its essence written on a distant, flat screen. This is not science fiction. The mathematics supporting this idea is robust and emerges from our attempts to reconcile gravity with quantum mechanics. The information that falls into a black hole does not vanish into the singularity. According to this principle, it is never actually lost. It is smeared and scrambled, but it remains imprinted on the event horizon itself, preserved in the microscopic quantum structure of that surface. When Hawking radiation escapes, it carries that information with it, not in a simple, readable form, but encoded within the intricate correlations between the radiation particles. The paradox dissolves because the information was never truly inside the black hole to be destroyed. It was always on the surface, waiting to be slowly and chaotically radiated back out into the universe. Think of it like watching a movie. The rich, three-dimensional world you experience on the screen with characters moving in and out of rooms is not actually inside the television. It is all generated from the flat, two-dimensional data on the film strip or digital file. The black hole's interior is the movie, and its event horizon is the film. This principle suggests that the entire universe might operate on the same cosmic rule. We may all be living inside a hologram of staggering complexity, a projection from the edges of spacetime itself. The ultimate secret of a supermassive black hole may be its power to become a cosmic parent. Deep within its hidden interior, beyond the point of no return, the laws of physics as we know them cease to exist. In that realm of infinite density, some theoretical models propose that spacetime can undergo a profound transformation. The immense gravitational forces could cause the fabric of our universe to pinch off like a budding cell and seal itself into a separate, self-contained reality. This new region would expand under its own rules, with its own constants of nature, potentially giving rise to an entirely new cosmos, a baby universe disconnected from our own. This idea, known as cosmogenesis, suggests that every black hole could be a gateway to a new creation. The singularity at its heart would not be an end, but a beginning, a cosmic womb where the conditions for a new Big Bang are forged. In this breathtaking scenario, our entire universe might itself be the interior of a black hole residing in a much larger parent cosmos. We will be living inside a cosmic Matryoshka doll, our reality nested within another. This remains one of the most speculative ideas in all of physics, a thought experiment that stretches our understanding to the breaking point. There is no direct evidence, no experiment we can yet perform to test it. But the mere possibility forces a radical shift in perspective. The dark anchors at the heart of every galaxy might not be tombs. They could be nurseries, each one cradling the seed of a new reality, a separate universe with its own future, its own stars, and perhaps its own mysteries waiting to be born. These cosmic nurseries operate on a timescale beyond human comprehension, but the void also sends us signals on a human timescale, sharp and fleeting. Among the most puzzling of these are fast radio bursts. These are not the slow, deep songs of black holes, but incredibly powerful, millisecond-long blasts of radio waves that travel across billions of light years. For a single, brilliant instant, a fast radio burst can outshine 500 million suns, and then it is gone. Their origin remains one of the great modern mysteries of astronomy. While most are now linked to highly magnetized neutron stars, the possibility of a black hole connection still tantalizes scientists. Could some of these rapid-fire signals be the final death scream of a star being shredded by an intermediate mass black hole we have yet to find? Or perhaps they are generated by immense magnetic flares from a young, hyperactive accretion disk surrounding a newly awakened giant. The link is speculative, a cosmic maybe, but it highlights how any sudden, violent release of energy in the universe must be considered in the shadow of these gravitational monsters. While the search for a black hole source continues, a far more profound signal is waiting to be heard, one that is not a flash of light but a constant vibration in the fabric of reality. This is the gravitational wave background, the secret hum of the cosmos. Just as the air in a bustling city is filled with the combined murmur of countless conversations, the space-time around us is thought to be constantly rippling with the combined echo of every supermassive black hole merger that has ever occurred. It is a low-frequency rumble, a chorus of cosmic thunder from the collisions that built the giants in every galactic center. Our current gravitational wave detectors are deaf to this profound bass note. It is too low and too constant for them to pick out from the noise, but the next generation of observatories, like the Laser Interferometer Space Antenna, will be tuned to this frequency. Flying in the quiet of space, this incredible instrument will act as a giant ear, listening for the collective hum of the universe's foundational events. Hearing this background rumble would be like listening to the history of galaxy formation itself, a direct record of how the cosmic web was stitched together by the merging of dark matter halos and their central black holes. It would confirm that the silent anchors of today's galaxies were forged in the violent, noisy unions of the ancient past. The mathematics of a spinning black hole contains a pathway to the past. Deep within the warped spacetime of a rapidly rotating Kerr black hole, the equations of general relativity allow for something called a closed time-like curve. This is not a machine with dials and glowing lights. It is a path through the fabric of the universe that, in theory, loops back on itself, allowing a traveler to return to their own past. The engine for this bizarre possibility is the black hole's spin, which drags space-time around with it in such a violent vortex that the distinction between past and future could, in certain regions, become blurred. Think of it as a cosmic river flowing in a circle. If you could find a small boat and paddle hard enough, you might be able to travel upstream against the current, arriving back at a point you had already visited. This theoretical river exists inside the event horizon of a spinning black hole, a region where the normal flow of time breaks down completely. The very direction of time could become a spatial dimension you could literally walk along, tracing a loop that brings you back to a moment before you began your journey. Yet this mathematical marvel is almost certainly forbidden by the universe. The physical paradoxes created by such time travel are insurmountable. What happens if you go back in time and prevent your own birth? The logical inconsistency creates a universe-breaking loop with no resolution. Physicists believe that nature has a built-in defense against such chaos, often called the chronology protection conjecture. This principle suggests that as you approach the conditions needed to create a time machine, quantum effects would always conspire to destroy the pathway. The energy densities would become infinite, or a wall of radiation would form, vaporizing any would-be time traveler before they could create a paradox. The black hole, in its relentless enforcement of cosmic law, would rather tear apart the fabric of reality than allow a contradiction to exist. So while the equations on a page whisper of fantastic journeys through time, the universe itself seems to shout a firm and final no, preserving the one-way arrow of time as the most sacred rule of all. The final secret is the most humbling of all. We have only just begun to understand. Every discovery peels back a single layer of a cosmic onion, revealing a new level of mystery beneath. Each of these 50 secrets, from the galactic anchor to the quantum whisper, is not an end point. It is a doorway into a darker, deeper forest of questions we have not yet even learned how to ask. The true nature of the singularity, the resolution of the information paradox, the possibility of other universes, all of these remain veiled in shadow. Our current knowledge is a single candle flame in an infinite cavern, illuminating only the ground directly at our feet while the vast, echoing darkness stretches on forever. Yet this is not a cause for despair. It is the spark of a new golden age of exploration. Our tools are evolving at a breathtaking pace. The Event Horizon telescope that gave us our first ghostly portrait of a black hole is expanding, adding new observatories across the globe. Soon, it will capture not just a static image, but a movie, showing us the turbulent, real-time dynamics of the accretion disk and the chaotic dance of light around the photon sphere. We will watch the void in motion, and in the pristine quiet of space, a new ear is being prepared to listen to the universe's deepest rhythms. The Laser Interferometer Space Antenna, LISA, will detect the low-frequency gravitational wave background, the constant hum from the mergers of supermassive black holes across cosmic time. We will no longer be limited to the sudden chirps of stellar mass collisions. We will hear the slow, stately boom of the true titans as they spiral together, a chorus that has been ringing since the first galaxies formed. These new senses will not give us the final answers. They will shatter our current understanding, presenting us with data that defies our models and forces us to think in ways we cannot yet conceive. The ultimate secret of the supermassive black hole is that it is a perpetual teacher, and its greatest lesson is that the universe is far stranger, more wonderful, and more mysterious than we have ever dared to dream. Our own bodies carry the echo of these distant giants. Every single breath you take contains oxygen atoms forged in the heart of a massive star that lived and died long before our sun was born. But the story goes even deeper than stardust. The iron that carries life, giving oxygen through your veins, the calcium that strengthens your bones, and the gold that adorns a ring. all owe their cosmic abundance to the most violent events in the universe, events choreographed by the silent gravity of supermassive black holes. These giants did not forge the elements themselves, but they set the stage for the cosmic forges that did. By governing the chaotic centers of galaxies, they orchestrated the collisions of neutron stars, the very events that create the heaviest elements through rapid neutron capture. The gold in a wedding band was likely born in the furious aftermath of such a collision that may never have happened without the subtle, gravitational nudges from a supermassive black hole over millions of years. We are not just living in a galaxy anchored by a monster. We are built from the products of its influence, the very spiral arms of our Milky Way, the grand architecture that cradles our solar system, are shaped and maintained by the gravitational hand of Sagittarius, a star. Our place in this cosmic city, the rhythm of our galactic year, and the very atoms that constitute our existence are all part of a legacy written by the void. We look up at the night sky and see distant, terrifying darkness, but the profound truth is that we are intimately connected to it. We are the universe become conscious, gazing back at the very forces that sculpted us. The final secret is not about the black hole itself, but about us. We are the children of the cosmic abyss, living proof that from the most violent and destructive forces in existence can also emerge complexity, beauty, and life. This journey through 50 secrets brings us from the silent birth of giants in the cosmic dawn to the very edge of theoretical physics, where time and space lose their meaning. We have seen how these invisible anchors dictate the fate of galaxies, forge the elements of life, and whisper their existence through gravitational waves and quantum tremors. They are not just objects in space, they are the ultimate expression of nature's extremes, laboratories where the known laws of the universe are tested, broken, and perhaps reborn. To study a supermassive black hole is to probe the deepest boundaries of reality itself, to ask questions that challenge our most fundamental assumptions about existence. We have stood at the precipice of wormholes, witnessed the birth of new universes in theory, and grappled with the paradox of information screaming from the void. The exploration has only just begun. Every answer unveils a deeper, more beautiful mystery. Now we turn the final reflection over to you. Of these 50 incredible secrets, which one reshaped your understanding of the cosmos the most? Share the secret that amazed you in the comments below. And if your curiosity for the universe's grandest puzzles is not yet satisfied, subscribe to continue this journey into the unknown.